Okay, so looking at 7.5, hypothesis testing for variance and standard deviation. So here we're looking at critical values of chi-squared tests. So remember we looked at chi-squared is like our fancy cursive x squared. Okay, so in real life, it's often important to produce consistent, predictable results. For instance, consider a company that manufactures golf balls. The manufacturer must produce millions of golf balls, each having the same size and the same weight. There's a very low tolerance of golf balls for variation. If the population is normal, you can test the variance and the standard deviation of the process using the chi-square distribution with n-1 degrees of freedom. So we have two key things here. Our population has to be normal, and again, we're going to use n-1 degrees of freedom. So when we're finding our critical values, we have our steps. First thing we always want to do is we want to identify alpha. And then here we're going to also identify the degrees of freedom. And remember, we use n-1 to find that. Then for step 3, we're going to be using table 6. To find chi-squared, and then we're going to have subscript 0 to represent the critical value. And we're going to have 3 different ways we look at this. So the first one is if we're right-tailed. We're going to use alpha with degrees of freedom n-1. Okay. If it's left-tailed, it changes slightly. And we're going to use 1 minus alpha with degrees of freedom n-1. And if it's two-tailed, we're going to use half of alpha with degrees of freedom n-1 and 1 minus half of alpha with degrees of freedom n-1. Okay, so remember chi-square distribution, it's not symmetric, so we're never going to have a positive and a negative. All of our critical values will be positive. So if we look at this example, find the critical value chi-squared value for a right-tailed test when n equals 26 and alpha equals 0.1. So since it's right-tailed, we know we're just going to use the alpha that's given, and then n equals 26 means that our degrees of freedom equals 25. Okay, so knowing that, if we look at table 6, okay, one thing that's really helpful is up here. This will help you remember for right-tailed and left-tailed if you're doing alpha, or if this is our left-tailed, this would be 1 minus alpha. So that's an easy way to remember. And then notice on the right, 2 tails is 1/2 alpha on both sides. Okay, so let that help you out when you're finding those critical values. So we're looking for when alpha is 0.1 and our degrees of freedom is 25. So if we look, 0.1, 25, it looks like we get 34.382. Okay, so that's example 1. Okay, example 2, it gave us, let's see here, we're looking at left-tailed, and n equals 11, and alpha equals 0.01. So what we're going to look at here, we want degrees of freedom of 10, and if alpha equals 0.01, and if it's left-tailed, we want to look at 1 minus alpha, which would equal 0.99. So if we look at that, 0.99 go down to 10, and we have 2.558. Okay, in example 3, if we, let's see here, we are two-tailed. With n equaling 51, which means our degrees of freedom is 50, and alpha equals 0.01. So remember, we're going to have two different ones here. We're going to do 1/2 alpha, which gives us 0.005, and then 1 minus half of alpha gives us 0.995. So going through and looking, so degrees of freedom of 50 is down here at the bottom. And if we look at 0.005, we get 79.490. Okay, and then for alpha 0.995, our critical value would be 27.991. Okay, so that's how you find your different critical values. So note, because chi-squared distributions are not symmetric, remember we're not going to have positive and negative. Whenever we're doing two-tailed, we'll have two separate critical values that aren't similar. Okay. All right. So back to our notes. Okay. So chi-squared test. So this is kind of reviewing our steps of hypothesis testing. So the chi-squared test for variance and standard deviation is a statistical test for population variance or standard deviation. The chi-squared test can only be used when the population is normal, the test statistic is s squared, and the standardized test statistic, chi-squared, equals the quantity of n minus 1 times s squared over sigma squared. Okay, and that follows a chi-squared distribution with degrees of freedom n minus 1. All right, so our guidelines are our steps. So first, we want to verify the population is normal. Then we're going to state the null hypothesis, the alternative hypothesis, and the claim. And then we're going to identify alpha. Then determine the degrees of freedom, n minus 1. Then we're going to use table 6. I apologize now if you can hear Roxy snoring. To find the critical value or values. Remember, that is our chi-squared subscript 0. And then once we find our critical values, we can determine the rejection region. Or regions if it's two-tailed. We're then going to calculate standardized test statistic. And remember, that's our formula, n minus 1 times S squared over sigma squared. Once we know our test statistic, we can make our decision. And then lastly, like normal, we will interpret the decision. In context to the claim. Okay, so our normal steps that we've been doing, the only ones that are really different here is we're going to use degrees of freedom n minus 1, which is what we looked at when we were doing t-distribution, and then using our new table 6 that we used when we did confidence intervals in chapter 6. Alright, so looking at our first example. A dairy processing company claims that the variance of the amount of fat in the whole milk processed by the company is no more than 0.025. So one thing I do suggest is that you somehow mark your variance or your standard deviation, because it's going to vary from problem to problem. And since we're talking about variance, I'm going to go ahead and put our sigma squared. Okay, and it says that the company is claiming no more than 0.25. So no more would be less than or equal to, which would be our null hypothesis. And that makes our alternative hypothesis greater than. So from there we know we're going to be right-tailed. Okay. So you suspect that this is wrong and find that a random sample of 41, so n equals 41, which means that our degrees of freedom is 40, has a variance, since it was a sample, S squared equals 0.27. At alpha equals 0.05, is there enough evidence to reject the company's claim and assume it's normally distributed? Alright, so we've done the first few steps. So now we need to find our critical value. I'm going to go ahead and sketch our graph so we can put in our critical values with our rejection region. It's right-tailed. And remember, with right-tailed, we're just going to use alpha. Okay, so if we look at table 6, at alpha equaling 0.05, at degrees of freedom of 40, our critical value we get is 55.758. And then now we're going to find our test statistic, chi-squared. Remember our formula, n minus 1 times s squared over sigma squared. So this formula is using our variance. So degrees of freedom is 40 times s squared, 0.27, over sigma squared, 0.25, and that is approximately 43.2. So 43.2, that would fall to the left of our critical value, which means our decision is going to be fail to reject. HO. So interpret the claim. So if you need to, use that table I gave you in your notes last week. So at 5% level of significance, there is not enough evidence to reject the claim what's here? That the amount of fat is no more than 0.25. So looking at our next example, the company claims that the standard deviation of the lengths of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4. So if we go ahead and state our hypothesis, standard deviation, so we know we just have sigma, is less than 1.4, so less than would be our alternative hypothesis, which means that our null hypothesis is greater than or equal to 1.4. A random sample of 25 incoming telephone call has a standard deviation of 1.1 minutes. So at alpha equals 0.1, is there enough evidence to support the company's claim, assume the population is normally distributed? So we have stated everything we know. So our degrees of freedom, we can say, is 24. And since our alternative hypothesis is less than, that means we're going to be left-tailed. And when we're finding our critical value for left-tailed, we're going to do 1 minus alpha, which gives us 0.90. All right, so if we look at our table 6 for 0.9 for alpha and our degrees of freedom of 24, we get our critical value, chi-squared subscript 0 equals 15.659. Now we want to find our standardized test statistic. Here you have to be careful. So we know n minus 1 is our degrees of freedom 24. But then remember the formula is s squared. We're just given the standard deviation 1.1. So when you plug that in your calculator, make sure you square it. And that's going to be over 1.4 squared. So if you plug that in your calculator, and I'm just going to round to the nearest hundredth, we get 14.82. Okay, so looking at our graph in our rejection region, 14.82 falls to the left of 15.659, which means we're going to reject our null hypothesis. So at 10% level of significance, there is enough evidence to support the claim that the standard deviation is less than 1.4 minutes. All right, and our last example. A sporting goods manufacturer claims that the variance of the strengths of a certain fishing line is 15.9. A random sample of 15 line spools has a variance of 21.8 at alpha equals 0.05. Is there enough evidence to reject the manufacturer's claim? Assume that the population is normally distributed. So here we're looking at variance. So that means we're looking at sigma squared. And it says that the variance is 15.9. So that's going to be our null hypothesis, which means not equal to 15.9 is our alternative, which tells us off the bat we're going to be two-tailed. Alright, our random sample is 15, which means our degrees of freedom is 14. And our sample has a sample variance of 21.8, And we're looking at when alpha is 0.05. Okay, so if we make our graph, and we're looking at two-tailed. So remember, for two-tailed, we're going to take half of alpha, which would give us 0.025. And we also take 1 minus half of alpha, which is going to give us 0.975. Those are going to be our two values that we look at with our degrees of freedom of 14 at our table. So if you do that, you're going to get our critical values of 5.629. And the second critical value is going to be 26.119. Now we want to find our standardized test statistic, chi-squared. So n minus 1 is 14 times s squared, 2.18, over sigma squared, 15.9. And if you plug that in your calculator and round to the nearest hundredth, you get 19.19. So that value falls in between our two critical values, which means that our decision is going to be fail to reject. Okay, and our interpretation says at, how about not point, let's do 5%. There we go. Level of significance. There is not enough evidence to reject the claim that the variance is 15.9.